Good evening, everyone. Am I audible? Good evening, everyone. Am I audible?
You're audible, sir.
You're audible.
Yes, sir, you're audible.
కొంచెం రీసౌండ్ వస్తుంది సార్ వెంకటేష్ సార్.
అవునా? Good evening, respected dignitaries. Professor P. Somaraj Garu, Secretary and Correspondent, Gayatri Vidya Parishad. Professor P.V. Sharma Garu, Director R&D and founder of Gayatri Vidya Parishad. Chief guest, Sri Radhakrishnan Pasirajan Garu, former scientist, ISRO. Professor K.S. Bose Garu, Principal, Gayatri Vidya Parishad College for Degree and PG courses. Professor P.V. Vinay Garu, Director, Engineering and Technology Program, Gayatri Vidya Parishad College for Degree and PG courses. Professor S. Krishnaveni Garu, Coordinator of the program, and Dr. P. N. Nageswarrao Garu, HOD, Department of Electronics and Communication Engineering. Distinguished faculty members and dear participants. Myself, I am S. Venkatesh, Assistant Professor and Co-Coordinator of the program from Department of ECE, Gayatri Vidya Parishad College for Degree and PG courses. It gives honor to extend a warm and heartfelt welcome to all of you for ATAL-sponsored online 6-day faculty development program on Outlook on best practices and strategies for chip design implementation from industry perspective, organized by Department of ECE, Gayatri Vidya Parishad College for Degree and PG courses. That's fantastic, having 179 faculty members and research scholars from various esteemed institutions across India attended to our ATAL-sponsored faculty development program. Speakers to the program's quality and reputation. Now, I request our faculty development program coordinator, Professor S. Krishnaveni Garu, to address the participants.
Thank you, Venkatesh, sir. Respected dignitaries, Secretary and Correspondent, Professor P. Somaraju, sir. Director R&D, Professor P.V. Sharma, sir. Principal, Professor K.S. Bose, sir. Director ENT Programs, Professor P.V. Vinay, sir. Head of the Department, ECE, Dr. P. A. Nageswarrao. Today's chief guest, former scientist of ISRO, Sri Radhakrishnan Pasirajan Garu. My dear colleagues, staff, and esteemed participants of today's session, good evening to one and all. I am Dr. S. Krishnaveni, Professor in the Department of ECE and Coordinator for this FDP. It gives me an immense pleasure to welcome you all to the inaugural session of 6-day ATAL-sponsored faculty development program on Outlook on best practices and strategies for chip design implementation and industry perspective. First and foremost, I would like to extend my heartfelt gratitude to AICTE for sponsoring this program and for their continued efforts in fostering innovation and excellence in teaching and research. I would like to express my heartfelt gratitude to our management for their unwavering support and encouragement in organizing this faculty development program. This FDP has been meticulously designed to provide insights into the best practices and strategies in chip design implementation. A stellar lineup of experts from academia and industry, we will explore a broad spectrum of topics, including design methodologies, optimization techniques, challenges in testing and verification, and emerging trends in this field. I'm very much confident that this program will be a rich learning experience for all of us, fostering fruitful discussions and equipping us with actionable insights that we can take back to our classrooms and research initiatives. I would like to express my deepest gratitude to our esteemed speakers, Sri Dilip Yenni Garu, Sri K. Srujan Garu, Sri K. Uday Garu, Sri T. Hari Garu, Sri Raja Garu, T.P. Raviteja Garu, and Ms. Rashmi Garu for accepting our invitation to this FDP. Your contributions will definitely enrich this program and inspire us. Thank you, everyone. I wish participants all the best. On behalf of Department of ECE, I express my heartfelt thanks to our beloved principal, director, and management for their encouragement support for organizing this event. Thank you, one and all.
Thank you. Now I request Dr. P. Nageshwar Rao Garu, HOD, ECE, to address the participants.
Good evening. Honorable Secretary and Correspondent, GVP, Professor P. Somaraju Garu. Founder member of GVP, Professor P.V. Sharma Garu. Principal of the Institute, Professor K.S. Bose Garu. Director, Engineering and Technology Program, Professor P.V. Vinay Garu. Coordinator, Professor S. Krishnaveni Garu. Faculty members, participants. On the outset, a warm welcome. I welcome you all for the 6-day faculty development program on outlook on best practice and strategies for chip design implementation from industry perspective. Gayatri Vidya Parishad College for Degree and PG courses is established in the year 1988-89. And the engineering college in this Gayatri Vidya Parishad has been established in the year 2011. And this is the first of its kind which is established an engineering college in the hub of degree and PG courses in the year 2011. The institute is approved by ACT, autonomous and permanently affiliated to Andhra University, accredited by NAC twice, and the Department of ECE has been accredited by NBA in 2019-20 and reaccredited by NBA 2020-23. So this is one of the youngest college or institute or department which has been accredited by various boards of NBA or NAC. The department has started in 2000, as I said, with an intake of 60 and later propelled to 120 from 2022 onwards. The department regularly revises the curriculum of the syllabus as per the guidelines of APSI NEP policy of 2022 and periodically takes the inputs of the industry and make the students globally ready and make them successful in getting placements. The department has got excellent infrastructure and state-of-art laboratories. And we always look forward to conduct these type of activities. I would like to mention this is the second ATAL FTP sponsored by ACT to our institute. Earlier, one of the ATAL FTP we have conducted during the COVID, which was a grand success. During then also, Professor Krishnaveni was the coordinator. And now we are sanctioned one more ATAL FTP to be conducted by ACT. I extend my heartful thanks to ACT and my management members for having been given this opportunity for hosting 6-day ATAL FDP. Thank you one and all, and make the most benefit out of this workshop for all the participants. Thank you.
Thank you, Nageswara sir. Now I request Professor P.V. Vinay Garu, Director, Engineering and Technology Program, Gayatri Vidya Parishad College for Degree and PG courses, to address the gathering.
A very good evening to all the dignitaries, Professor Bose Garu, Professor Somraj Garu, Professor Sharma Garu, and Professor Krishnaveni, Professor of Department of ECE, and P.A. Nageswara Garu, Assistant Professor and Head Department of ECE. It is a nice initiative that ECE department has taken up. We would love to see more and more coming from the department, and especially on the subject that you are going to deal with in the next 6 days. Chip design has become one of the important things to be ready with. Unless and until you niche it, there is going to be a serious information scenario that is going to come across, so that whenever there is a new technology that comes in, unless and until you make a design which is right and you manufacture it and sell it across into the environment, you cannot test it. And at the same time, unless and until you follow best practice, you would usually yield, or you would usually have a lot of environmental impact too. Hope this 6-day FDP is going to give you a huge insight into different strategies that you will have to look at in design, as well as the best practice that you will have to look at. Thank you so much. Hope you learn a lot from this.
Thank you, sir. Now I request Professor K.S. Bose Garu, Principal, Gayatri Vidya Parishad College for Degree and PG courses, to address the participants.
Thank you, Mr. Venkatesh. Good evening, one and all. Respected elders, our President, Professor P.S. Rao Garu, President of the Gayatri Vidya Parishad, and Professor P. Somaraj Garu, Secretary and Correspondent of Parishad, and my mentor and my teacher, Professor P.V. Sharma Garu, economist, one of the founder members of the Parishad, and coordinators of this today's inaugural session and today's 6-day workshop, faculty development program, Professor Krishnaveni Madam and Mr. Venkatesh, and resource persons and industry experts and participants. Good evening, one and all. It's a great pleasure to take part in this event, because this chip designing and chip design implementation and from the industry perspective is the present day buzzword in the entire the world right now. And many supply chains relating to the different products are directly or indirectly linked with this a small component. Many economies are trembling, and many economies are nowadays focusing on developing and designing these chips. There may be many global factors, economic factors, geopolitical factors are influencing and focusing on to this particular small component like the chip. Even in India, our esteemed Prime Minister Modi ji focusing much on this particular sector, Semicon India. Central government has outlaid around 1 lakh crore rupees towards the development of the chip design ecosystem in India. There are a lot of many opportunities that are available for the many youngsters to get the good placements, good job opportunities, as well as to become a successful budding startups and entrepreneurs. I appreciate my colleagues, Professor Krishnaveni Madam and Mr. Venkatesh, to take up this particular topic, which is highly crucial at the crucial time and the right time. Definitely, I assure you all that participants that definitely this particular 6-day program add value to your career and your knowledge base. Definitely, please take part in this and enrich your knowledge and actively participate in the discussions and deliberations and make this program successful. From the chair, and I really appreciate all my industry colleagues to take part in this, to share your knowledge and experiences in the industry to our budding teachers and experienced professors. And finally, I thank the AICTE and my management to handle this particular program in a successful manner. With these few words, I once again I welcome you all for this particular inaugural session and FDP 6-day online FDP program. Thank you, one and all.
Thank you, sir.
Thank you, sir. I am very honored to introduce today's our chief guest, Sri Radhakrishnan Pasirajan Garu. He is industry veteran with 35 plus years of experience. Initially worked as scientist in ISRO for more than 5 years. He is core founding team member of Open Silicon India handled the VP role. Prior to this, he had extensive working experience in US Silicon Valley Bay Area during 90s, held various engineering responsibilities and executed more than 150 chip tapeouts in his career. Thank you very much for accepting as chief guest, sir. Now I request our chief guest, Radhakrishnan Pasirajan Garu, to address the gathering.
Am I audible?
Yes, sir, you are clear.
Okay, thank you, Mr. Venkatesh. Respected dignitaries present in this session, the principal of the college, professors, assistant professors, and faculty members who have joined this session, this FDP program from various colleges. I assume you have come from multiple part of Andhra, and industry leaders and the scholars who are present in this session. I wish to pass on my hearty greetings to all of you in this evening. Actually, it is a great pleasure for me to be part of this faculty development program, especially addressing such a large faculty member gathering. I have delivered lectures and technical lectures in various other FDP programs, but I have not heard of a 6-day long program with that too. The count said 179 people, 179 faculty members, and also there are a lot of scholars. Really happy about it, and that shows the seriousness of this effort and the interest that everyone is showing up to understand, learn, and also pass it down to the young engineers who are graduating. I'm really happy about it. I'm happy that I'm also part of this gathering. So this whole program is about revolving around the VLSI industry. Today, if you take the various state-of-the-art, cutting-edge technologies that is happening, you can name a lot. And 5G is happening, IoT is happening, quantum computing, blockchain that leads to these cryptocurrency and things like that. And you take the automobile engineering, there is a lot of ADAS, which is automated cars, like driverless cars. These are all various things that is happening around. But I will talk, my speech today, I want to really channel it towards the VLSI industry and also about the chip making. I will give a very generic overview of that so that you get an idea before you get into the real crux of the various techniques, methodologies, and techniques that are followed. So I will talk about that. Maybe I'll take about 15 minutes or so. I hope that's okay. In all these technologies that I mentioned, which is going to be the cutting edge technologies that is going to change our life also. The way we do things, the way we connect with people, the way we talk to people, there's a lot of things that's going to happen. And in every aspect of this, electronics is going to play a major role. It has been playing a major role, and very specifically, chip making is definitely going to be a major component, major ingredient in all these evolutions that are going to come. So let's just look around, take any device that is around, pick anything, be it your microwave oven or a washing machine in the kitchen, or your electronic watches, the cell phone that you normally, nowadays everybody carries a cell phone. It's a smartphone, right? Pick up and take a look at it. Every one of these devices has a lot of electronic components, and to be very specific, they are having something called SoC, which is a system on a chip. That's what the term that we normally use. It is not just one single function, but it is an integrated, complex functions are integrated into it, so that many of those functions can be performed. One part is doing that job, and the second thing is how well it is able to do and how reliable they are going to be. See, cell phone is a very common it's a very common device that everyone has, but there are many other areas, all the way from a simple toy to a very complex space launch vehicle. There is electronics plays a major role. So the integration of discrete components is what eventually evolved into a form of an integrated circuit. More and more compaction. The technology that drove us from very old technology, for example, 25 years back, we used to work in 650 nanometer technologies. Today, if you talk about it, we are talking about 3 nanometer or 4 nanometer or even 2 nanometer technologies. What it means is the transistor sizes have shrunk from 165 nanometer transistor. Actually, it means the channel length of the transistor has shrunk to an extent that it is multi-fold miniaturization has happened. So such a development has led to what are known as ASICs and ASSPs. ASICs are application-specific ICs, and ASSP are application-specific standard products. So the latest manufacturing technologies, and advanced capabilities have actually led to this revolution. If you look at around the world in the last 4 decades, right? In the last 4 decades, VLSI field has turned into flourishing, contributing, game-changing field. And in India, from 2000 onwards, roughly around 2000 onwards, for the last two decades or 2.5 decades, people have started getting VLSI specific work. What started as a verification hub initially, there is a lot of IPs in doing these devices. IP in the sense intellectual property, right? So in those days, in early 2000s, the design houses which are there abroad, mostly in the US, were very hesitant to even send their codes, their RTL codes, in fear of infringement. But that's how it started with the verification hub. But later, if you see today, we are doing everything that is possible in the chip industry, everything from start to end. As Professor Bose mentioned, government of India is very serious about building the ecosystem for the semiconductor industry, and there is huge talks that are going on, making the foundries, even getting the foundries in place. Tata has come up and set up a huge packaging house in the outskirts of Bangalore, and Tata is actually doing a foundry in Assam. You may all be knowing about it. So this eventually will close the ecosystem, and India will be able to provide a 360-degree coverage for all the aspects of silicon engineering. Okay. I actually want to spend a few minutes talking about why do we need an ASIC? ASIC in the sense, be it an ASIC or ASSP. Why at all we need it, right? There are a few reasons why people tend to go for ASICs, and the very the first thing that comes to the important thing on this is in the olden days, many of those functionalities were done in software. Algorithms were written in software and they were run in certain CPUs, and it takes about say few microseconds or few milliseconds to complete the task, be it a simple addition or a multiplication or whatever it is. Later, we started moving these applications, these algorithms into the hardware. We started finding the hardware equivalent of these requirements and started implementing in the what is known as the hardware description languages. Some examples are Verilog and VHDL. So when implemented in hardware, the kind of improvement in performance is manifold. What used to take a few milliseconds, few tens of milliseconds, can be done in about a few hundreds of nanoseconds. So that is one reason why people started doing ASICs. The other thing is the miniaturization. You take any device, the amount of volume, the ratio of the volume that is provided for the electronic components in a product is actually small. This means that we will not be able to make huge circuits in place where there is the space is a constraint. For example, a good example is the cell phone and say the earbuds that you use for listening to music and things like that. So miniaturization is another important drive, which was scaling again with the transistors also. Transistors also scaled from 650 nanometer all the way to 2 nanometer. Similarly, the products also are becoming compact, more compact and compact, so that the demand, the requirement for putting more and more logic in a lesser area or lesser volume became important. So that's another reason why we go for ASICs implementation. Then the power reduction. Larger circuits with the huge circuit boards and large electronic components used to take a lot of power. Whereas the ASICs, when you implement, the power reduction is another major advantage for which we go for ASIC implementations. Another thing that I want to say is about the cost. When you go for large productions, actually there is a cost impact to it. Cost effectiveness that comes into it, and that is also helping. And the last one, which is very important, is the security of the IPs. I mentioned about the intellectual property theft, right? When a software code is stolen, it is stolen, and then somebody may be able to reproduce it or modify it a little bit, and they will be able to use it. Whereas in a silicon, when you implement a code and it is implemented as in the form of an ASIC, what is available to you is only certain X-ray views of the transistors. For somebody to reverse engineer and get it to a functional mode, it's going to take ages. So these are the reasons why chips are being made. In industry, what actually the industry is looking for when an engineer is designing an ASIC. This is important to know, and that's what all the lecture series that you are having in this program, in this faculty development program. Various industry leaders are going to talk about how things are being done. But I will put down the challenges that are in front of the engineers so that you will be able to understand why somebody is doing something and what part of the challenge they are addressing. The first and foremost is the performance. When you say performance, every product company that is wanting to deliver or release a product wants to make sure that their product gives the best experience, best user experience to the customer. Let me again go to the cell phone analogy, because you take a cell phone which is an Apple. There are multiple brands, right? There is an Apple, there is an OnePlus, there is a Nothing, there are Redmi, and there are other categories of devices. So where do we want to, what do we want to have in our hand? Probably we want to have a best experience. Good visual, good audio, good connectivity, and of course, best pricing also. So this is what we look at, right? Of that, the performance, it is applicable to the laptops. Somebody who are buying a laptop, he always wanted to go for the highest performing, the best performing laptops. So, when you talk about performance in the silicon, in the silicon, what is driving the performance? It's the frequency of operation. The basic engine that's actually working is driven by a clock frequency, and if a device is working at 2 gigahertz, that's supposed to do certain million instructions. Let's say we talk about the CPU, it is supposed to do certain million instructions per second. Whereas the same CPU, if it is able to operate at say 2.5 gigahertz or 3 gigahertz, obviously the performance of that device will be higher. So this is one of the basic parameters that is put in front of an ASIC designer, chip designer. So it has to be delivering a highest performance. So we call it as PPA, power, performance, power, and area. The second P stands for the power. Imagine your cell phone need to be charged 4 times in a day. Do we like it? Will we ever be buying that kind of a cell phone? But remember, in the early 80s, the first cell phone that was designed by Motorola Ericsson, it had a battery life of half an hour. It has to be charged for 4 or 4.5 hours. It has to be charged, and then it will live for half an hour. So imagine that kind of a situation versus what we are having today. We have devices which can be used continuously for at least a day, and depending on the application, it can even come for 2 days or 3 days. So power optimization is a second basic criterion, one of the criteria that is set in front of the ASIC designer. He has to design the circuit so that it takes the least amount of power. There are several power saving techniques. In a complicated chip, there are certain areas which are not used, can be switched off automatically, dynamically. You can switch off or switch on depending on the requirement. So those kind of advanced techniques are all available, which the industry leaders will be talking when they are talking about the methodology. So I mentioned about performance, I mentioned about power, and the third thing is the area. I told about it, but area. Why is area important? When I say area, it is the square millimeter. We have a wafer, and in that there is a die. The smaller the die, the lesser will be the manufacturing cost. In a given wafer, when the die is smaller, you'll be able to make more number of dies. So that means your productivity is higher. Whereas if your die size is bigger in a given wafer, there will be less number of chips that you'll be able to get it. So area is also put as one of the important criteria in front of an ASIC designer. So what he has to do is to put more and more compaction, more and more devices, which means like millions and millions of transistors are to be packed into a given square millimeter. That's what is the next challenge. How is he able to do? There is something called utilization in a given die. If you have 100 square millimeter die, if you can populate your devices, say, into the 85% of the area, because some area is needed for routing, connecting the networks and things like that. So you will not be able to place 100% of the area. You cannot place the cells. Usually the tendency is to have about 75% utilization. It's a really good implementation. So if you can make it even more, then your cost is going to go down. So that's how it is connected. So this PPA eventually is looked at as the parameters for a design engineer. I actually add another parameter called scheduled. If you're given infinite amount of time, if you're given say 4 years for developing a chip, probably we'll be able to meet all these requirements because our schedule pressure is not there. Whereas in the industry, there's something called time to market, and if you don't tape it out on time and release the product on time, we are actually going to lose the business. So many companies have gone bankrupt because of this kind of problem. Their first chip that they did would not have worked, or it would not have come on time, so they lost the marketing window. So schedule is also important. So if you look at, we have performance, power, area, and schedule. And the first three parameters are closely interlinked. For example, if you want to improve the performance and if you increase the frequency, increasing frequency will increase the dynamic power, which means the power is going to go high. And if you want to put more and more logic into the die, it's actually going to affect the power. More logic means more power. And more logic will also affect the area. You cannot compress beyond a point. So all these things are very closely interrelated. And when you're optimizing, the techniques that we are using to optimize these devices are actually connecting all these three factors. And of course, I have added schedule also on top of it. All of you might have heard about Moore's law, right? So Moore's law, fortunately, is holding good even today, and the technology scaling that the industry has brought has actually been has done wonders. Even about 6 or 7 years back, we were dealing with 65 nanometer and 45 nanometer technologies. Suddenly, these foundries have made a semiconductor technology group has done wonders. Today, we are dealing with 4 nanometer, 3 nanometer, and even 2 nanometer designs. Intel is right now working on 1.8 nanometer, 18 Armstrong unit design also they are working on. So the transistor scaling is has been really tremendous and supportive for making this whole ASICs world even more challenging. What is another limiting factor in the industry is the lithography, the light that is used, the light wavelength that is used for lithography doesn't allow going beyond certain dimensions. But people have circumvented that with different kind of technologies. Today, if you talk about 3 nanometer, 4 nanometer technologies, we have something called multi-pattern. So you creating a one layer of inference, you can actually do multiple masks. And the logical operation between those two patterns will eventually end up in a smaller dimension on the die, so that you'll be able to manufacture that die. So those kind of technologies are there. While I'm talking about technology, it will be very unfair if I don't mention about the EDA industry. EDA is that electronic automation, design automation industry. Those are the people who actually come up with the tools that is used from top to bottom, from start to end. EDA industry has been catching up with the technology development. The technology people will come and say, I can manufacture a transistor with a 3 nanometer channel length. So you have to deal with the dimensions of that small in nature. And the EDA tool also should be able to complement that and then support that kind of design implementation. There are various errors that can creep in if the simulations and the extractions analysis are not done correctly. So EDA industry takes a lot of pain to make sure that there is reality. Whatever they are doing is a lot more real, and there is good correlation between what is seen in simulations versus what is actually being seen in the silicon. So we should give a big applause to the EDA industry also. So for students who are working, who are studying in the VLSI stream, they will have a very good opportunity to go into the EDA industries also. There is a lot of opportunities in the EDA industry too. Okay, so today, you all may be hearing all the time about artificial intelligence and machine learning. So that buzzword has not left the VLSI industry also. Everywhere there is a lot of experience that's happening that actually makes the things fast forward. That's what this AI and ML is doing. What it needs is a set of learning platform where the tool, the software, the AI agent can learn a lot of things and then redeploy the learning in an optimal way, so that we'll be able to solve the problem in a faster manner with multiple choices. That's what is a large target of this AI/ML. We have also started looking into using AI and ML in various aspects of silicon implementation. It starts from verification, finding out the test cases, that coverage, then placing the devices, placing the transistors, routing, and better clock tree implementation. Like in every area, AI is being used. It is actually picking up, and the EDA industry also has picked up a lot in the AI, and they're also doing a very good job. Okay. So that is about what is actually being asked for in the industry. What are the challenges set in front of us, so that all engineers, I mean, what are they solving on a day-to-day basis? Apart from the technology that they are solving, how do we implement those technologies in an ASIC? So that's what I talked about so far. Let me slightly talk about what the students. What is that you can take back to the students? I always believe that the fundamentals are the building blocks for any engineering, any stream of engineering. So students need to be very savvy on their fundamentals, be it the Thevenin theorem or Thevenin equivalent or the Boolean equations. I mean, all that we are doing in digital in the VLSI industry is all solving the Boolean equations. When I came into the VLSI industry, we used to write the equations by hand. We used to write the Boolean equations by hand and then give it to the compiler to synthesize it. But today, there's a lot of high-level languages that are available. Even a C-like program, or even the higher-level programs, can be converted using compilers into a machine level coding, and then which can be converted into an equivalent Boolean expressions. That's what happens. But if you look at today, the students, today's young engineers, mentality is that they are very dynamic. They are very dynamic. They want to do several things. They want to put their hands everywhere. So probably that aspect of that attitude also can be used towards flourishing in what we are actually doing. So today, focusing on one thing is not going to be very helpful. You need to be looking at everywhere to find multiple solutions for a given problem. And obviously, for every solution will have multiple solutions, and every solution has an alternate. So that is the attitude that we can inculcate in today's young mind. Make use of their dynamism, and inculcate that habit of bringing automation into the flow, bringing artificial intelligence, and doing things in a faster manner with a lesser interaction. Those are areas where we can actually enable the students, so that they, in addition to the fundamentals and understanding the logic behind and understanding the theory behind the ASIC implementation, they can do certain additional things also. That's what industry also is looking for. Okay. Yeah, somebody's raising a hand. We'll do it. I'll be done in another 1 minute or so. After that, we'll talk about. Okay. So that is what I prefer, that the students, as faculties, you go back to the students and inculcate these habits and these in the students. And academia and industry, when I talk about, I just want to have a few words on academia and industry. There was a huge gap in between the academia and industry for a very long time. But nowadays, I see that the gap has been really reduced. Big thanks to this EDA industry, and they have given those softwares to many colleges, either at a very less cost or maybe even free, so that these engineers can be trained in those tools, and they are becoming industry ready. There is both advantage and disadvantage in that. The advantage is that the guy is already industry ready, and he is familiar with what he has to be doing, and he has a good hands-on experience while he is in the college. But the disadvantage I see personally, I don't know whether how many of you agree to it, is that he is only focusing on that, and his vast knowledge and his imaginations are all restricted, and then he's actually focusing on that particular thing. Initially, what actually happens is, after the studies, we go to the industry and then orient ourselves in a certain field, and then we improve our skills to do better in that area. But here, these kind of pre-preparations while the students are in the college is having a negative effect. Is also is my personal view on that. But no matter what, these Thevenin equivalent, Maxwell theorems, and your analysis of circuit theory, everything is necessary, and somebody has to understand completely for doing really good in their career too. One last thing I want to mention is about the trend that I see in the engineering education. We see that there is lots and lots of engineers are graduating every year, and I'm finding that going to colleges and interviewing students for placement, I don't find a lot of. There is a cream of the crop is always there. But it is very unfortunate that many of the engineers, the real understanding of the engineering education and contributing towards their engineering capabilities is actually missing, is what I see. That may be because there are so many colleges, so many, the quality of education, all those things matter, is what I think. And also there is another aspect of employability. I mean, when the parents pick the colleges itself, they are talking about employability. I think at the beginning of the education, if we start talking about employability, I feel that the orientation and the focus of the young mind is actually getting distracted. This is my personal view again. So with all that said, I think I wish all the faculty members to grab a lot of these good learnings from the industry veterans who are all here, and then pass them down to the young engineers. With all that said, I come back to my role of inaugurating this FDP. So I formally declare that this 6-day FDP program on outlook on best practices and strategies for chip design implementation from industry perspective 2024 is inaugurated, and I wish all of you the very best in the coming 6 days for the maximum learning and happy learning. Thanks a lot, everyone, for having me here and patiently listening to me. Thanks a lot.
Thank you so much, sir. Really, it's a very informative and interesting session. On behalf of Department of ECE and all participants, I extend my heartfelt gratitude to our esteemed Chief Guest, Radhakrishnan Garu, for delivering such a thought-provoking keynote address at today's Faculty Development Program. Sir, your comprehensive insights on topics such as advancements in mobile technologies, network systems, and the relevance of Moore's law in the today's technological landscape were both enlightening and inspiring, sir. The depth of knowledge and practical perspectives you shared have provided us with a clearer understanding of the challenges and opportunities in the rapidly evolving field. Thank you, sir. We deeply appreciate your valuable time and expertise, which have undoubtedly enriched this program and inspired us to explore these topics further in our professional endeavors. Thank you once again for your gracious presence, sir.
Sure. Thanks a lot. My pleasure.
Thank you. Dear participants,
Somebody raised a hand, and maybe if they have a question.
Yes, you can speak. The participants, you can share your thoughts.
Okay. Okay. Someone was raising a hand while I was talking, but that's okay.
Yes, sir.
Yeah, Chandrasekhar.
Hello. Good evening, sir.
Right.
Am I audible? So,
Yes, sir. You are audible.
You're audible.
So I want to know that in mixed signal designing means IC designing, there are certainly two parts. One is the analog and another is the digital. So we are talking about the lower technology node, like 3 nanometer, and you are telling and talking about the 1.8 nanometer. But for analog design, just like your IP design purpose, so we are not going for the very much lower technology node. So what is
Yeah.
the reason behind this? Why we are not going that much? Because generally I have seen in the research paper, they are doing working up to the 90 nanometer or 45 nanometer up to.
Yeah. So see, digital is more, I mean, it is self-explanatory, I would say. Digital is very discrete. So you are able to go make the whole logic work faster and faster by making the by making the clock frequency higher and higher, and by going to a lower node, smaller nodes, the delays that are associated with that is going to reduce further. Okay, this is the very nature of a flip-flop or a gate, a digital gate that is sitting there. Whereas in an analog circuit, today, if you're making an op amp, it is actually producing the resolution which is very, very high, all the way from 0 volt to 5 volt, and you don't need a refined technology for that, right? So analog is analogous, and you are able to produce that with a lower technology node. Going to a medium type of technology node. Going to a higher node is actually a cost implication is very, very high. So something done in 180 nanometer versus what you are doing in 4 nanometer is actually going to be probably 10 to 15 times more expensive than what one would do at a 180 nanometer. So there is no need for going to a high. I mean, why do we go to a lower node? It's for the faster speed of the digital logic of the gates, right? Whereas analog circuits are analogous in nature, and they can be done with the higher nodes, higher in the sense larger nodes. That's why you don't find many mixed signal designs, I mean analog designs going into that. It's basically transistors that are operating and just to generate the continuous voltage variation for various functions. And the fidelity of that is what is more important than doing things at a much faster manner. Whereas in a digital circuit, you can actually operate at a very high frequency.
Okay, nice, sir. Thank you for your answer. One more thing. Is this compatible to design the same type of different technology node in a same chip? Because analog we are using some higher technology node, and for digital this is good. But in the same chip we are using the same type of
No.
different technology. Yes.
No, you cannot do that. I mean, it has to be a different die. But nowadays, what people do is they actually do the designs. Because of these demands, IPs are also analog IPs are also getting into the smaller nodes. You cannot mix technology types, but in a package, you can have two different dies. One die made out of 4 nanometer, another die made out of 150 or 180 nanometer. And then you can make them to talk through certain things called interposers. Using interposers, you can actually connect two dies. 2.5D and 3D techniques are there, where you can have multiple dies in a given package, in a single package, and yet make use of the functionality. I mean, that's one technique that people use to come up with the cheaper solutions. But all the IP companies are actually going and making their IPs. For example, SerDes. So the smaller the transistor, the faster they are able to operate. Able to operate. We are making 25 gig and 25 and 28 gig SerDes and all are being made in 4 nanometers and 3 nanometer technologies. So it's evolving, but you can't have two different technologies in the same die. You cannot have that.
Okay, sir. Thank you very much, sir.
Sure. Okay. I hope with that we can conclude. If there are no questions, Dr. Krishnaveni.
Thank you, sir.
Okay.
Thank you, sir.
Good evening, everyone. It is my privilege and honor to deliver the vote of thanks for this inaugural session of our faculty development program. On behalf of our Department of ECE, I extend my heartfelt gratitude to everyone who has made this event possible. First and foremost, I would like to express a deep sense of gratitude to our chief guest, Sri Radhakrishnan Pasirajan Garu, former scientist at ISRO, for taking time out of their busy schedule to grace this occasion. Your insightful address and valuable on VLSI have set an inspiring tone for this program, sir. Thank you for sharing your expertise and motivating us. I express my deep sense of gratitude to our beloved secretary and correspondent, Professor P. Somaraj Garu, Director R&D, Professor P.V. Sarma, sir, Principal, Professor K.S. Bose, sir, for encouraging us to conduct this innovative session. A special thanks to our Director, Professor P.V. Vinay, sir, for their unwavering support and encouragement in organizing this FDP. Your vision and guidance continue to inspire us in our academic pursuits, sir. I also extend my heartfelt appreciation to resource persons who will be sharing their knowledge and experience over the course of this program. Your commitment to the teaching and research community is commendable, and we eagerly look forward to gaining valuable insights from you. My sincere thanks to the organizing committee members for their meticulous planning and seamless execution of this program. Your dedication and teamwork have ensured the smooth conduct of this session and will absolutely continue to drive the success of this entire FDP. Last but not least, I would like to thank all the participants for joining us today. Your enthusiasm and active participation are what truly make this program meaningful. We are confident that the coming days will provide each of us with opportunities for growth, collaboration, and innovation. I would like to extend my gratitude to AICTE for sponsoring this program. Once again, I thank each and everyone for your presence, contribution to this event. Let us carry forward these insights and inspiration gained today into the rest of the program. Thank you, one and all.
Thank you and all the best, madam. Thank you very much.
Thank you.
Thank you, sir.
Thank you, all of you. Bye-bye.
Thank you, sir. Now, I request G. Saujanya Lakshmi Madam to introduce today's speaker, Dilip Yenni garu.
Good evening, respected dignitaries and my dear faculty members. It's my privilege to introduce speaker of today's session, Sri Dilip Yenni, Technical Manager, West Global-Hyderabad. He has decade of experience in VLSI backend implementation, and over the years, he has worked on multiple programs at various levels, progressing from engineer to tech lead, then tech lead, and ultimately to his current role as a tech manager and program manager. His extensive experience spans critical areas of project execution for global clients, which include renowned companies such as AMD, Intel, Infineon, LG Soft, Texas Instruments, L&T, Cadence, and MediaTek, as well as other clients based in the US and China. His expertise covers the entire spectrum from synthesis and DFT to GDS delivery across technology nodes ranging from 90 nanometer to 3 nanometer. Thank you so much for accepting our invitation, sir. Now I request Dilip Yenni garu to address the gathering.
Handing over the session to Dilip garu. Dear participants, a feedback link will be shared in the chat box. And we request everyone to be stay in the meeting throughout the sessions. 80% attendance is compulsory to get the certificates.
Yeah, thank you very much, madam. And special thanks to, am I audible? Hello?
Yes, sir, you are audible.
Thank you, Madam Krishnaveni. Yeah, I would like to firstly thank the management of Gayatri Vidya Parishad for allowing me and giving an opportunity to contribute for the uh, contributing for the benefit of the faculty community and mm, performing our part from the industry to extend our knowledge and expertise for the next 6 days, or my role would be for this current today for the next 2.5 hours. We're going to interact, and mostly I wanted to put this as an interactive session, but rather I would first cover up with the content that I have as a presentation. Let me flash my screen, and before that, if you you can make me you can acknowledge if I'm audible enough, and let me first put on my video and say hi, and then we'll move on to the presentation. And with that, I'll turn my video off, and then we can continue. Yeah. Thank you for acknowledging. Yeah. Let me quickly share my screen. We can walk through the outlook and perspective of the semiconductor industry in my viewpoint, and what I've gained through in the past 10 years in the VLSI backend implementation space.
Sorry for interrupting you, sir.
Yeah, please.
Small announcement. Dear participant, all of you, please switch on your videos to take a screenshot. Please switch on your cameras.
Let me just quickly.
Participants, please switch on your cameras. Please, 1 second.
మేడం అటెండెన్స్ లింక్ చాట్ బాక్స్ లో కనపడలేదు మేడం, ప్లీజ్.
షేర్ చేస్తాం సార్.
ఓకే మేడం, థ్యాంక్ యూ.
Okay, sir, continue the session. Thank you so much. Dilip, sir, continue your session.
Yeah, thank you, madam. Yeah, let me just. Yeah, I think you should be able to see my screen now. Are you
Yes,
able to
sir.
see my screen? Please
Yes, sir.
acknowledge. Yeah. I'll firstly cover about the industry outline, and mostly it is in line with the academic books that we read through in the VLSI subject that even I studied during my time, like and further explain about where this VLSI technology is used, and also differentiate between what is ASIC and SOC, the front end and the back end flow that we have, and we'll deep dive a little bit into analog and digital background that's supposed to be having, and what are the different job role or EDA skill sets that will be mapped to each of these aspects in the front end and back end. Yeah, I'll as I walk through. So industry perspective, like academic point of view, we mostly have this VLSI known as a subject. Basically, it has evolved right from SSI to MSI and to now to the current VLSI. So SSI being the small scale integration with nearly about 100 transistors being packed onto a single area. So this all has happened with the invention of the transistor, dated back in 1940s in the Jack Kilby labs in the Texas Instruments, basically. And with that invention of the transistor, it has been evolving, and currently we are in the era of very large scale integration. And in between, there are examples we can quote. The first SSI had an example of one logic gate being put onto the same aspect ratio, currently what we use. And in the medium scale integration, we had the basic Intel processor. This is during the 1970s time frame, but still that is how the technology has evolved. And currently we are in the era of the Intel processors, the core processor or the server process that we use with 32-bit and 64-bit configuration. And this is how the VLSI inception has happened. As we get into the next details, how the industry is trending and the projection that we have for this particular VLSI industry in the coming decade, and where do we stand as of today. The VLSI industry is spanning across all the areas, like for example, as the faculty experts have mentioned, it is into communication and it is into automotive area. And basically we find the application of this VLSI technology, especially like for example, we take a communication 4G or 5G modem, modulator, demodulator that we call it as. For example, we have chipsets from big companies like Qualcomm or MediaTek, wherein they have a SoC being sitting in there for the purpose of this high frequency band spectrum processing. And that is how our telecalling communication happens. And these are the different examples. In the next slide, also I have certain specific chipsets or SoCs that are in this specific area are also mentioned in the next slide. But to give an overview of where this industry is trending and where all these applications are present, I put in this particular slide. If I wanted this session to be a little interactive, and if you have any questions, you can bring in or raise your hand, or we can put the entire questions to a question and answer session in the very end. But since this is a very long session for 2 hours, you can rather put that as interactive one. You can pitch in between and then ask your questions as well. So automotive, as Radha Garu also mentioned, the ADAS is one of the technology which is very much prevalent. Autonomous driving cars. So these are the prevalent technologies in automotive, wherein this VLSI features are being used, and IoT or even home automation has the VLSI technology being used, and supercomputing servers, mega servers, which operate on a very high volume of data computing, are also having this chip present in them, basically. And AI dependent models, like for example, the Bitcoin algorithms that are being run are having this AI models to be put on a SoC, and then there are multiple functions out of it. So currently, as of now, this is a this is again, it's present on the internet and it is being as a viewpoint put onto this slide, but still the current trend of the market, as you see here, and the year 24 is nearly $750 million. And it's going to be close to about $1.8 trillion in the next decade. So it's going to be a very happening industry, and a lot of focus is being put onto every aspect of the design making. There are a lot of research and R&D research and happening in this area, and a lot of products are coming out from this industry. If any questions here, I can take it. Otherwise, I'll move on to the next data. So what are the VLSI use cases? Like if we talk about the mobile SoCs, as I mentioned, for communication purpose, every mobile that we use, like for example, the medium that we are using for connecting today's session, the FDP, we are having a high-tech super processor sitting inside the mobiles or even the laptops, right? In the mobile point of view, like for example, it's an Apple, it has a Bionic chip, and for Qualcomm, it has a Snapdragon, and MediaTek, it has Helios. And these are all the variants of their SoC and the naming that the convention that they would give for their products, each organization, right? And they are all specifically built in for the performance purpose. They're built in a certain technology, and that is how the variants would evolve. For example, Apple 13 version and next version is the 14, 15, and the latest one is 16. Every particular version has a different chipset in it, and that is being graded with a lot of features being added in it, or even in the back end, the technology is also changing. What is this backend technology that is changing? We will look at in detail in the next content. But otherwise, the mobile SoCs are a very undetachable part of our life, and now we have been sailing with that, all this leverage that we have. And the complex microprocessors, like from the AMD and the Intel, those also have this particular VLSI, miniaturized technology. Automotive MCUs, like for the infotainment purpose, ADAS, and automatic braking system. There are all automotive MCU players like the TI, Renesas, Infosys, NXP. These are all the different automotive chip makers. These are all different organizations and across the industry that we have. And these are the major players in the industry. Most of them might not be known by our regular community because these are all very niche and only players in the VLSI space. There are different categorization of whether they are a fabless or a fab-based company, or what kind of difference that they make. We have that in the next slides. We will go through that. We will go into that details as well. And AI and ML based processors, every pacemaker or Bitcoin or these kind of products definitely need a certain technology chip that makes this function. So there are other vendors, other players in this area who brings in this kind of products: Broadcom, Analog Devices, NVIDIA. And yeah, these are the various applications that I put. But still, what is this all about? This technology is all about having the transistor miniaturizing. We have, we generally study in the academic world, it is about the planar FET, the MOSFET that has a, in general, we deal that as a 3-terminal device, but rather that is a 4-terminal device with the body or a bulk being tied to the respective potential, highest potential that could be. So as we look at this particular device here, This is a planar MOSFET with a source and drain, which is identical, and it can be interreplaceable with the oxide layer differentiating the thin channel and then the poly on top of it. That is the gate, we call it as. So that is how the control happens for this planar MOSFET.
Hello, Dilip sir.
Hello, Venkatesh sir, am I audible?
Yes, sir. Audible.
How long it's been? I'm not audible. How much time it's been?
Just 1 minute.
1 minute, okay. We have covered this part, VLSI technology dependency. I mean, this particular area. I was talking about
No, sir.
the
Not
MOSFET being a planar device. We generally study that as a 3-terminal device, but it is a 4-terminal with the fourth one is the body or bulk tied to the respective potential, the highest potential.
No, sir, up to planar device you have explained, sir.
Yeah, planar device, right? So later on, the technology has now evolved, and the evolution is now termed as the 3-dimensional device, that is the FinFET. From down to 16 nanometer, we are using this FinFET technology with a more control on the channel, with the gate being as a U-shaped device. So it is a 3-dimensional, and most of our academic research community members from the faculty as well would be well versed about this FinFET, I believe. So it need not be specially introduced, I think, but I do not have a picture of FinFET here on my slide, but still, this is a planar FET, and the crux or the bottom line of the entire VLSI story begins with this FET operation understanding, and this makes the device working at a higher speed based on our requirements. So when we scale down from a 180 nanometer down to 5 nanometer, 2 nanometer, the performance wise, it is increasing. There is a high performance linear curve, as you see here on the graph. This is the graph that depicts the performance metrics and the power metric here. And as we trend from 180 down to 2 nanometer, we are getting a lot of added value benefit. That is the performance wise. Performance is the switching rate, right? The amount of time it takes for turning on and turning off. It acts as a switch, and then a lot of bits are being passed through. It's either a 0 or a 1 that can be processed by this transistor. It's happening at a very instantaneous rate. So that is the performance, the way I define it as, basically. And as this miniaturization is happening down in the 3 nanometer or 5 nanometer, a lot of throughput is improving for the entire system. Preferably the high-tech computing, or in these applications like mobile SoCs or complex processors, AI processors, would definitely prefer or take up this lower nanometer technology for implementation. But for safety reasons, to my experience, automotive is still sticking to higher technology nodes, or there is a power constraints or even in the industry, usually like all the automotive players are still with the 65 nanometer stable designs. Like they do have analog component on the design. Analog is still not miniaturized to this level, 3 nanometer, be it the operational amplifier or current mirror circuits. The gain controlling
Sir, Dilip sir, again you are muted, sir.
I think you see it on my screen, right, Venkatesh sir? It's not myself I'm muting, but someone is trying to mute me. If my discussion seem to be very boring, let me know. I'll refrain from doing that. But someone is muting me. Please let me know if there is any concern.
No, sir. By mistake, they have done it.
Sure. So as we scale down from 180 to lower technology for till 5 nanometer or 2 nanometer, the performance is definitely increasing, and this is what is depicted here. Yeah. Any questions here? I'll be able to take. If not, I'll move to the next slide that I have. Yeah, I'll quickly walk through what is this ASIC flow. ASIC is it's a well-known acronym for the full form Application Specific Integrated Circuit. And what is the SoC is the system on chip that we are dealing with. So basically, I wanted to introduce the mixed signal ASIC or SoC flow. Is both the analog and digital being present on a single die, and how do we deal with that kind of design. And I wanted to explain what is the difference between a full custom and a semi-custom design. In general, the categorization that we make. In the full custom design, usually it is more of like a handicraft. It is hand woven. And the analog design would fall in the full custom design category. Analog design or be it the standard cell design, PDK development, all of this work falls in the full custom design. So it is once for the initial time, it's once for all. It will be reused in the semi-custom part. So usually, whatever IP development that happens will happen as a full custom design category. So both of them has a front end and a back end barrier. Like what differentiation basically front end and back end, how it is being differentiated will get to know now. In the analog design, we usually have the analog system design, that is the analog or radio frequency memory design and its simulation that will take part. And examples of this analog design would be the SerDes or any of the high-speed DDR5 interfaces that we design, and the PCI Express and basic amplifiers and the clock generator units, the PLL and voltage controlled oscillators that we put on the chip basically. These all are designed in the full custom design, analog design part. And in the back end of this particular full custom design, we have the analog layout, which is usually performed with very much customization. That is completely hand-drawn. The layout is hand-drawn. And usually in the academic curriculum or syllabus, we would have topics like the stick diagram understanding, stick diagram bring up for gates in the sense of the logic gates, basically. That is a part of the standard cell layout design. analog is more precise in manner, and it deals with a lot of concepts in the analog layout. And even in the standard cell design, it happens once for one technology. That is the PDK development that we call it as. PDK is the process design kit for a specific technology. It can be developed by any of the organization. Like basically, there'll be different vendors of this PDK. The PDK initial data will be coming from something called as foundry. I will explain this pyramid, and then we'll go a little bit in detail about understanding of different players in this particular area, and then we will understand more. But otherwise, in the back end, the PDK development part is nothing but the standard cell designing and development part. And similarly, memory IP layout construction and IOs and RF layout. Basically, this deals with the high-speed IO interfaces that is present on chip to interact with the external world and get back the data on chip. This design happens separately as a custom design. This is all analog in nature. The entire thing is analog in nature. And in the semi-custom design, if no questions on full custom design, we'll move on to semi-custom. If you have any questions, I'll be able to take here. Anyone would like to ask any question? Or you want to put all the questions at the end, and you can ask at that time, but still I wanted to have this more interactive. So Krishnavini ma'am and Venkatesh sir.
Sir.
Yeah, I think this is mostly covered in the academic interest,
Yes,
right? So is this already a part of our existing curriculum, or still this is something above and beyond? I wanted to know if that is being conveyed, the message is conveyed up to the level of expectation.
Yes, sir. Yes, sir. Actually, it is there in curriculum.
Okay.
Okay,
So,
if you have any doubts, you can ask. Otherwise, you can write it in a message.
yeah.
If you can't speak, you can write it in a message.
I'll be able to explain a little more in detail about physical design with this particular about the backend design, because that is where I come from, backend of digital design. I'll explain a little more in detail about this in the next slide as well. But still, this gives a complete overview and understanding of what this full custom and semi-custom is, and especially how the design flow and the program cycle, right? How a product will evolve out of the entire process across different players in the industry. Yeah, let me cover up certain more detail, and then we'll move on to the questions if there are any. Yeah. In the semi-custom design, we have the digital design, right? So this is mostly reuse of the existing IPs, be it the standard cells that are designed in the full custom design, or the IP like the memories, on-chip memory that we would be using on the design. We will consume that into the digital design as an IP and start constructing our product. Like it begins with the architecture selection, the digital design. Basically, if we would think about a product, for example, we are talking about a SIC, like only a specific activity should be performed by in the product, in the system. Then we would have the very basic controller architecture, or the advanced architecture might not be needed there. The architecture selection is very much needed and it's important there. For example, instruction set architecture. Like you might have heard about ARM Cortex kind of architecture that will be present in the mobile processors. That is the RISC architecture we generally talk about. And the complex instruction set architectures are the von Neumann architecture, basically, which are used in the still till date in the Intel processors, the Intel Core i3 or Core i5 processors, which would be using the complex instruction set. And architecture is the instruction cycle organization or arrangement, how the communication or even the data packets passaging happens, right? And this is all planned at this stage. And once at this level it is completed, they would go into the planning of the microcode or the microarchitecture. And that is performed with the help of our HDLs. That is the HDL is the high-level description language or hardware description language. That is basically a Verilog or a VHDL code that we have. And the verification will be followed for this code. So verification has different streams. Verification basically is performed in a system Verilog language. And it is usually writing a test bench environment. It is creating an environment and passing certain vectors to the system and observing the results on the output. Like it happens with a lot of rigorous testing, and there are different methodologies even for verification that are present. Like we call them as the OVM, UVM. These are all the advanced methodologies which would require for testing. And even the RTL design is not simply a microcode that would evolve, but it is for example, for an SoC, we would need a different components present on a single chip that needs integration. For example, there is a piece.
Dilip, sir.
Hello.
You are muted, sir. Please unmute yourself.
I don't know what's happening here.
Once I will check the control settings, sir.
Yeah, you can check that. Maybe. Yeah, thank you. So I was talking about the verification, different methodologies that we have, and if at all for an SoC, we have different IPs like PCIe, DDR. These all need to be integrated with different bus communication protocols like AMBA, as you know, and even the network on chip, the CAN, or any of these interface communication protocols, right? And all of these need to be verified thoroughly before and so once the RTL is designed, it need to be it can be checked or prototyped. Basically, on the FPGA, we prototype it, and the emulation will be performed. So basically, this is not a complete silicon model, but still the performance of it can be observed in the FPGA part. So from this, the RTL design, the synthesizable RTL code will be taken for the backend implementation. And from here, the entire backend digital design cycle would follow. Like the synthesis is converting the HDL into gate level form. This purely as we write our Boolean equation, the expression will be converted into a logic gate form with basic principles like SOP, POS. We use sum of products, product of sums, and all of the principle. And that if it is done with the synthesizer engine with advanced tools like the EDA tools that we use, and that is performed at this stage in the digital implementation in the synthesis. And similarly, we have another domain called as the DFT, design for testability. And here we would have a number of requirements. DFT is basically for the purpose of testing the chip post silicon. Once this design is manufactured and we get the die back, we need to package it, and then we should be able to test and find the faults where exactly the silicon might be going wrong, at which particular node or which particular point. That feature or technique of testing should be implemented during the time of design itself. Pre-silicon itself, we need to perform that. For that purpose, there are several methodologies or techniques that will be used in the design for testability, and that will be an integral part of the chip design backend. And once we have the design for implementation, that is, we call it as the physical design. The entire cycle here is the physical design cycle that we have. I'll explain it in little more detail, and then we'll move on to the sign-off aspects. So once we have the netlist as an output from synthesis, we perform the, basically this is the design entry phase. This has been explained, like the chip specification and verification. RTL synthesis is what we're dealing with. So synthesis is converting HDL to gate level form, and once we have the gate level form in an output called as a netlist. Netlist is the connectivity of logic gates, and usually the name netlist has evolved because it is information about nets, and net is a component which is a physical form of a wire. Wire is basically, in the RTL code, we define it as with a wire, right? It's a connectivity between points. So here net is a physical form of connecting between pins, as we call it as the standard cell logic gate, pin to pin connection. There is a net. The connectivity information of the nets is present in the netlist. So netlist will be taken for design planning in the physical design. So I will cover a little bit more in detail in this particular sheet, but as we have it here, first we perform the partitioning of the chip. So when we say about partitioning, it is a top-down approach. So we have a very bigger size die, and that need to be planned in several smaller portions. Then we perform a procedure called as partitioning of this particular die, planning of what size each block, we call it as a block. Each part of that particular die will be called as a block. How much size the block should be, everything will be planned in the stage of partitioning. With that, we can have DFT also integrated for each blocks wise, and basically the netlist is cut into several blocks, and DFT also can be inserted in the netlist stage. And then we move on to the stage called as the floor planning. Floor planning is again where we have a lot of memories on chip. As we discussed, reuse of this customized IPs will be performed in the digital design. And customized IP, one such mostly used customized IP will be the RAM, on-chip SRAM, static RAM. So SRAMs will be for the purpose of storing and retrieving the data, quickly processing on the chip itself. It will be used. And those SRAMs will be, for example, it is in the configuration of, like, there is a 2 MB that is needed on chip. 2 MB will be configured, broken down into a number of KBs. That is 2 MB is 2048 KB, right? And that will be broken down into a lot many number of basic trivial configurable RAMs, like 256 by 256 bit, like that kind of configuration. And we might end up in having 20 or 50, or maybe at times, based on the size of the memory that is needed, we might have 100 memories, 100 RAMs on a single block if needed. So 100 blocks, that is 100 memories that we have on the in a particular block need to be planned for floor planning. So the floor planning will happen for placing all of these memories in the periphery, and we basically plan the design in such a way it is completely data flow driven, how the data will enter into the block or into the chip and how it will pass out of the chip. Based on that, we will plan our memories also. So there are certain guidelines for floor planning, and which will also be covered in the next slide that I'll explain in detail. But still, this is the floor planning stage that we have. And as the technology shrinks, we are coming down from 90 to 45 and down to 28, or the current 5 nanometer or 3 nanometer that we deal with. The number of rules or care that we need to take here in the floor plan stage will increase. There is a tremendous increase in the number of rules that we are supposed to follow while performing the floor plan, actually, in the lower nanometer technologies. And from here, it is all tool automation. It's completely tool driven. From here, the next stage is the placement stage, the placement optimization. It's automatically done by the tool with the internal algorithms. And it is a single cockpit command that we'll be having in any of the EDA tools from any of the vendor. And that will make the entire placement of standard cell logic gates onto the given space. Like that is the die area, we call it as. Die area internally will be having a core area for placeable standard cells. So inside the core area, all of the standard cells will be placed actually with a single command, and that will be driven with other constraints also. Other constraints or other parameters when we call, it will be timing driven and power aware also. So when we say timing, there are other concepts that will be associated with that. We'll talk about it in a little more in detail, but still we'll move through this particular diagram first, and then we'll cover that in detail in the next slide here. And so once the placement of standard cell is performed, and then we'll move on to the clock tree synthesis. So the beauty of digital design is it can be completely controlled by a single signal called as the clock. Whether you want to turn off the entire design or turn on, making it active and performing, it can be done by having the clock correctly balanced. And that is performed. The balancing is something that brings in a lot of concepts like the skew or latency control. And these are all different keywords that we use in the implementation in order to meet timing requirements. When we say timing requirements, it is basically either the setup time requirement or a hold time requirement that will be present for a digital circuitry that need to be met. So that happens in the every stage, but still in the clock tree stage, we build the clock tree, clock propagation, clock build happens, and the propagation also happens in the CTS stage. I will explain a little more detail, like with the one of the die being shown, and then we'll move into intricate details of this CTS also. And once the CTS is completed, there we have connecting all of these standard cell logic gates with the technique called as routing. When we have routing is nothing but it is connecting the pin to pin, the nets basically, in specific allocated layers. So for any technology that we deal with, there will be a specific number of layers to route these nets, and that we call it as the metal scheme or a metal basically the we call that as a metal scheme. How many number of layers that can be used in the specific technology? For example, 3 nanometer or a 5 nanometer basically we deal with will be using up to 15 metal layers, or it can use up to 18 metal layers. as the number of metal layers is increasing for your specific design, the cost increases. As the area of the size increases, the cost increases. So everything is dependent on the cost parameter. So size of the design and number of layers also will limit you from planning your budget actually for this particular chip or a design. So that is how the number of layers might be at times restricted. It will be based on our logic code also, code efficiency. So a lot of parameters will be acting here for planning one particular design, and one such is the number of routing layers that we'll be using. Usually the thumb rule is if there are 9 metal layers, for example, there are 9 metal layers in the design that we can use. The top layers, top 2 to 3 layers will be used for power routing. Intermediate layers will be used. The next immediate layers from 8 and 9 will be used. That is the 6 and 7 will be used for clock routing, clock net routing. And the bottom layers usually will be used for the signal net routing, the data signal net routing it will be used for. So this is the thumb rule we generally follow. And that is how the designs will be implemented. There is a purpose also to do that, and it will be talked a little more in detail. As we conclude this, once the routing is performed, we optimize the design further and optimize for the purpose of timing and setup time and hold time requirement. So every stage we can perform incremental optimizations here. So that is all completely tool driven, and based on the design complexity, the runtimes also matter. Usually the process might take a little more time if the number of logic gates we are dealing with are more. For example, a typical design usually in the recent times can be of 1 million instances. 1 million instances is nearly, you can account for the number of standard cells that will come out. 1 million instances can be dealt based on the design complexity. Placement can be roughly about 6 to 7 hours. It is again based on the complexity, and CTS can be for a couple of hours. Routing can be for a couple of hours. It is on the memory machine configuration also that we have. So this is all completely tool driven, and so at every stage we perform optimization, and finally at the post route we will have our outputs being taken for the purpose of final verification. That is the sign off verification we call it as. As I walk through the complete physical design flow, that we call it also as the PNR, place and route flow. We can move on to the sign off now, that we call it as signing off this chip and the back end in different aspects. That is timing aspect, power aspect, the IR drop is the reliability, the way it is robust. We can guarantee whether it's robust or not. It can withhold, the chip can function for how many years, like how much lifespan can be there. That all can be validated at this stage. And the physical verification is the there are certain rules that comes from the foundry which need to be obeyed, and then the layout need to be performed. These all will be checked at this stage, at the sign off stage. So each stage has its own tool set, and it needs its own expertise. It comes with several years of involvement in the design and performing that activity devotedly. And each role is handled by each engineer. And there is a sheet in the next slides as well, which will explain which tool will be used where and who performs what kind of a role. Whenever we perform a STA work, that is called, the engineer is called as a STA engineer. And we perform a PV work, that is a physical verification engineer. So there's a lot of classification of the roles that will be performed by team members in any particular program. That is how it is configured. So whenever these aspects are need to be dealt, it needs a fundamental understanding of these concepts. When we are talking about timing, so in the academic curriculum as well, there are basic concepts like digital circuitry, right? You have the differentiation between combinational, sequential elements, like even in the sequential, it goes up to the finite state machine understanding, and it's about the shift registers. All of this will be present. So fundamental understanding of concepts like the setup time requirement, hold time requirement, if it is well dealt in the academic time, like that is the college itself, it is being dealt, it will be very much easy for an engineer to understand these advanced topics once they enter this particular field. So my sincere request to all the faculty friends here is we'll go over certain specific list of prerequisites for any of aspirant to be a part of this particular field. If you can hone these particular skills in those those particular interested individuals, it will be very much beneficial for them, for the next generation who will be a part of this industry, right? And better understanding can happen in the initial stage rather than like they're struggling after entering into the field and then they're lacking the basics maybe. Then it will be a little tough. So I've talked about a little advanced topics till now, but still these are all trivial. I've come across also certain colleagues of mine who have been a part of Gayatri Vidya Parishad, and they've also mentioned the physical design also being part of their curriculum as one of the subject, I think. Am I correct, Venkatesh Garu?
Yes, sir. But it will read by some people. It is in electives.
Elective, okay. So if it need not be only physical design, but if it is in the RTL design or verification, so I'm very much happy that during our time, like back then, 11, 10 years back, there was no much outreach or exposure towards all of these topics, right? Now that we are able to get in front of everyone in the forum, we are able to understand and correlate to all of these topics. So if this is being very carefully taken to our next generation, that is the students who are very much interested in these topics, I feel there will be a fruitfulness out of this session. Yeah. With this, I would conclude. So final verification is involving this sign-off, and we would have the GDS, that is the graphical data stream format information interchange that we have. GDSII, that is generally we call it as GDS2, but it is information interchange standard. That is how the data is shipped to the foundry for mask preparation, and the GDS format. So once we complete a design, we call that as a tape out. So once the tape out is performed, it is completely on the fabrication side, and we have certain detail of the fabrication also in the next slides. We'll cover that up. And to explain this pyramid, right? If there are any questions still here, you can please feel free to ask. Do let me know. Yeah.
Sir, one question is there in chat box.
Oh, okay.
Can you give details about device modeling with nanosheet?
Nanosheet, okay. Madam Vaishnavi, and device modeling with the nanosheet specifically might deal with a research point of view, because I am not specifically from a PDK development or a R&D aspect of this particular piece of work. I might not be able to right away comment, but if needed, I can little get to know about it and then come back. But as of now, I do not have much data about this particular question. Device modeling is basically if we deal with any FinFET or a MOSFET device, it will be characterized. So we will characterize that and we will get to know about its performance. And usually it's calibrated as a P-cell construction, and that is how we make in any of the advanced tools, right? Yeah. But nanosheet, I'm not literally aware of it. I'm sorry about it. Yeah. Any other questions?
Sir, can we develop any algorithms for placement and all? These are automatically will done by the software, right? Hello, Dilip sir.
Yeah. Sorry, I was on mute. Yeah, so automatically by software, but still that is like reinventing the tool itself. So that needs a lot of basic. So automatic algorithms, so it can be doable. So if we are able to write a basic tool of placing a standard cell or even based on the net length, this needs a lot of acumen in scripting or programming language. So this entire tool set from any of the EDA vendor will be built on a TCL and a language known as the TCL, tool command language, TCL. So if we are very much proficient with the tool command language, we can build packages and models out of it. And there are advanced, like we can build the procedures out of it. Each process is each operation that is performed by the tool is a procedure innately itself. So the procedures need to be controlled and run through. So having this entire knowledge of having the scripting knowledge basically will help us to write the algorithms.
Okay, sir. Thank you, sir.
Yes, thank you. Any further questions I'll be able to take? If not, we'll move on to the understanding of this particular pyramid structure.
Sir, what is the procedure to check robustness?
Robustness, the term robustness means it's the power sanity you're asking, or there are, when we calibrate a design, right? When we calibrate, the measures should be precise. What are we measuring? We should know, right?
How many years the chip will work?
Okay.
How many years?
Yeah. For that purpose, we have something called as fit. A check called as a fit in the sign-off environment that we perform. Sign-off IR drop. That is failure in test. Fit is failure in test. So basically, when we perform this fit test, it will put the entire design into rigorous testing. It will put onto all the parameters. There will be different algorithms to test this, check this even. Based on the fit value that we put, it will give out. So it is all software driven actually. So it will tell, we can control this parameter and say, for example, 5 years is the lifespan of this. Whether the yield of this will be relevant to that or not. So there will be techniques to overcome and improvise the lifespan of the design as well. Lifespan of this product, the chip as well. For example, if you have if it is going to work for 5 years, you can make that to 7 years or 8 years or 10 years by using a very robust vias or a better power mesh pattern. When we use for interconnecting the layers, right? There might be wear and tear or maybe misconnection of that over a period of time. That will not, the connection would fade away, just like our usual wiring, right? In the home as well, the wiring might get worn or torn, right? So similarly, on chip as well, the wiring might be broken after a certain time that is specified. In order to have the particular wire or interconnectivity between layers intact, we can use a double cut via. So there are multiple via structures that will be present. Via is connecting between two layers, one in the M6, maybe metal 6, and another one is in the metal 7, two different layers. It is equivalent to two different floors in a building, right? And whenever there is a via, if different kind of via or bigger via sizes are used, the lifespan of the design would increase basically. That is how the analysis will be performed. And we can say the robustness is preserved for the design. Hope that explains it.
Okay, sir. Thank you, sir.
That is one aspect and the sign off that we can deal with. If we move on to this different organizations that are being there as different players in this industry, what each of them perform. For example, whatever we design ultimately need to be manufactured and coming out as a product. That is the silicon wafer that we have. It need to be impregnated. The whatever mask that this entire thing is a mask. It will be shaped into a terms of mask. It is equivalent to maybe back in our childhood days, if we would have used something called as a stencil. A stencil is a in the colloquial language, if we talk Telugulo matladalante, achu pettalante, we use that stencil like 1, 2, 3. If we want to draw or ABCD, we want to put, we'll use the stencil. This mask that we prepare out of this layout is as good as a stencil. So whenever this stencil is there and in the entire process of manufacturing, that is the fabrication in the foundry, so these mask data will be sent to the foundry in the form of GDS, and this layers data will be sent to the foundry in the form of GDS, and the mask preparation will happen at the foundry's end. So major players in the foundries are like the line share of the entire foundry market is with the TSMC, that is the Taiwan Semiconductor Manufacturing Corporation, which is present in the Taiwan country. So basically, this is the major player in the entire foundry, with all the cutting edge technologies being evolving there. And it is the home for a lot of fabulous companies to have their products being manufactured by the TSMC. And apart from TSMC, we have other players like Samsung, Global Foundries, UMC, SMIC. These are all from different countries. The foundries are present. And that's only the foundry business, basically. Apart from this, Samsung is another player which has both its technology and its foundry ability with them. So when we have the classification, these are the fab-based company, only fab companies. And here we also have the fabless companies also. They only have a product, but they do not have the capacity of manufacturing them. The fabless company can be defined as they do not have the real wafer or silicon bring up technology. That is the entire fabrication unit they do not have. You could see on the screen, right? Similarly, there are integrated device manufacturers. That is both they have the technology and they can put their shuttle on their own time. When we call a particular product going for a tape out, we call that as a shuttle. When we say a shuttle, it can be started at any time. If it's for a multi-wafer per die, that is multiple products per wafer. So that is one form of a unit, like that is for the purpose of initial prototype building in the silicon. Test chips will be built with MPW format. That is, multiple dice will be put on a single wafer, and that will go for a test chip bring up. If it is going for a mass production, that will be performed at IDMs, and mass production is bringing up a particular chip with a lot of volume. A number of units are more. For example, Qualcomm processor is going to a OnePlus phone. OnePlus is going to bring maybe 1 crore units into the market in this particular year or beginning of 2025. This mass production need to happen for these chips first. And for that to happen, a lot of the shuttle would start at a specific time. And that is how the planning of the entire design happens. This is the product design life cycle, basically, in the aspect of chip designing, and a lot of tandemness. At the same time, the work need to happen, and planning in the design phase need to happen. Right from the beginning till the foundry chip manufacturing happens, and then the packaging happens, and the product comes back. All of this happens in the tandem, actually. So that happens very seamlessly in the IDMs. It needs a lot of association as well, right? From one organization to another organization, a lot of NDAs, and even a lot of association will be there. And that is how the products will be coming out in the market, right? And even the fab-based equipment. So there are different players in the photolithography aspect. These are the players which will bring in the technology of the reticles and all of this, right? Will be brought up by these organizations. So there is an interdependency between each of them, and the wafer supply materials and all of them will be dealt by these organizations. Similarly, we have the next one is the core key aspect is the EDA platform. So EDA, the major players has always been the Synopsys, Cadence, and then the Mentor now being called as the Siemens. Hunter Graphics, right? And now it's being called as the Siemens. It's been acquired by Siemens, right? And so all the front end to back end range tools will be provided by these players in the industry. And again, the IP cores, whatever we have dealt with this custom design, will be put as an intellectual property, and that will be reused by any of the player in the fabless or even in the IDM. So major IP players are ARM, and different analog IPs also will be present, and PDKs also will be present with these particular organizations. So there'll be a lot of association programs will be going on for one particular product to come out into the market. And we have these brands and well-known brands that will do this particular branding, and only we get to see is the front face is this particular thing, but behind this there is a lot of industry out there which will be every time in the high tech or a lot of activity would go in there, basically to get one product which is out in the market for us, for our benefit. And thanks for all of these organizations that has evolved and brought up a lot of products for mankind. Yeah, and this is what we have in the entire pyramid of VLSI, or basically the chip design bring up. And do let me know if there are any questions specific to this particular piece of data. If not, we'll move to a little more detail on the every aspect of the ASIC flow, front end and back end. If we are done with this, we'll move there. Any questions here? Yeah. Let me move on to the next slide that we have. What is the front end and back end differentiation? Already we have looked into that, but what is the interdependency that we'll be having? Where exactly we may need to turn back and then reevaluate the design, how we need to perform each stage meticulously so that there is no flaws in the design implementation or design bring up. So we'll understand that a little bit more in detail. So now if we begin with the design specification, so usually that is the spec that we have, and based on the specification, we will bring up our architectural needs and we would code our RTL, that is in the Verilog or VHDL. So we shall integrate all of this RTL code and a top will be made. That is the design top, we call it as associate top, a system on chip top or a design top. So design top, entire top need to be simulated and then it need to be checked on its performance. So the performance throughput will be judged here at this stage, and it has different metrics to evaluate here. Basically, the coverage will be considered here, and even in the verification aspect, we consider on the different coverages that we have. And as we simulate the design, these pieces of front end will be covered a little more in detail in the coming days. I think it is also planned as informed by Venkatesh Garu. But I'll mostly cover from the logic synthesis aspect and where exactly the feedback need to go to which team and which particular area, so that there is no issue in the implementation. So in the logic implementation viewpoint, we cover up with a lot of the code matureness that we have. So if the code, RTL code is nearly 70% mature enough, the code coverage, we call it as, basically if it is nearly above 60-70%, we begin with our logic synthesis. It need not be complete. The RTL need not be entirely complete. This is how the design cycle planning will happen. We do not wait for the RTL to entirely complete and then we begin with our synthesis usually. So it could be 60-70% mature and then we move on to our synthesis stage. So synthesis, as you know, I've explained, it converts the RTL language into logic gates form. And here we have the DFT technique also implemented. One of the technique is the scan insertion. Basically, we convert all the basic functional sequential elements into scannable sequential element. So when we say scannable sequential element, it is we can get a direct connectivity of all of these sequential elements. We can pass in our vector and get the output without touching any of the combinational element in between the sequential. So so it is a direct pass-through network that will be established in this scan insertion. So this is the technique of DFT. This will also be dealt in detail, I hope, in the next discussions that you'll be having. And in the logic synthesis and optimization, there will be furthermore detailed technique. Like for example, basic synthesis would deal with concepts like basic code elaboration. It would elaborate the design and it would convert it into a generic mapping format. So whenever you have AND gate logic written, a basic AND gate operation will be assigned to in the synthesis tool, but it need to be mapped to a particular technological standard cell that is present. This all happens with the set of inputs that we read for synthesis. So in synthesis, we would need the dependency of dot libraries. We call it as dot libs. Usually we handle the data in the form of libraries. That is, we call that as dot lib. Dot lib will be used for synthesis for purpose of logical mapping and area estimation and timing optimization. So these three aspects will be dealt when we read in the dot lib. Usually, I hope in the academic world, it will all be like a non-technology based synthesis will be performed, maybe in tools like Xilinx, Vivado. I don't think technology will be drawn. For example, library, if it is there, 45 nanometer or a 65 or a 28 nanometer technology, if it is used, the mapping happens. It's a technology dependent mapping will begin from there. And based on that, all the aspects of silicon bring up will begin in the synthesis stage itself. So synthesis as a concept in detail will be discussed, I think, in the next upcoming sessions in the next 6 days. But basic thing is it converts a software logic code into a logic gates form. It converts in the form of a logic gates, which are kind of visualizable physical in form. It has input and output relation we can establish in this format. That is, the output will be again netlist that we have. From here on, after synthesis, the data will be dealing in the format of netlist only. The logical connectivity format will be netlist. And apart from this, we have the entire design will be placed in certain condition. That is, it will be bound for certain constraints. That is nothing but the timing constraints we call it. So it will be based on a certain frequency of the clock. There will be certain exceptions for it, exclusion. Some exceptions will be present. So all of these will be handled with the SDC constraints. We call them as SDC, standard design constraints or synopsis design constraints. So design constraints will be put up for synthesis stage, and the optimization will be performed, and we even write out or bring out an SDC out of the synthesis engine, the tool. And these two input files, one is the netlist and the SDC, together we take to the further stages. So once we have synthesis completed, we will perform something called as a formal verification. Formal verification is something different from the functional verification. Is anyone in the team aware about formal verification? And anyone in the forum is aware about formal verification? What is exactly used or what is performed here? If you can type in, or if it is familiar to you, it is fine. But if not, I'll move on to the further discussion about these topics. But trivial difference, yeah, I think there is a typing. Yeah. No, it's not place and route. Formal verification means you need to check the logical correctness. It's also a verification, but it is a logical correctness of the design. The particular netlist need to be checked. So when we say a formal verification, we call that as a logical equivalency checking, LEC. Okay, logical equivalence. There is a RTL code that we have, and it is converted in the form of a netlist. So when we deal with RTL, it is directly having the simulation will be checked, and that is how we verify. But from here, the netlist point of view, it is converted in the form of logic gates, wherein a Boolean function will be present for each of the logic gate. For example, it is an AND gate. It will have A and B. That will give an output Z. That is how it will be end function. Every standard gate, standard cell logic gate that is used will have its own function in the .lib that we are reading. So based on all of these functions, we will pass on only ones and zeros as set of inputs. That will also be completely automated in a tool called as a logical equivalence checker. There are from different vendors, like from Cadence, there is a one particular tool, and from Synopsys, there is another tool for checking the logical equivalency. So it will be checked at this stage, basically between the RTL as one input and netlist as another input. It will check both of its equivalency, whether it is correct, it is equal enough, it is matching. When all of the ones and zeros are passed through inputs of these logic gates, and at the output, the correct function output is observed or not. So it all happens in the tool only. The tool also is written only with the ones and zeros understanding. So whenever a function is there, if you pass on 0 and 1, it's like interpreting the truth table. You have a truth table. Are you getting the correct output on the output side when you give a combination of 0 and 1 or not? That is only being checked in the formal verification by this specific tool. Any question here? So this is one of the important aspects in the entire backend implementation, and this itself is one person's job in the industry. There will be experts in the formal verification, LEC, logical equivalence checking. So that is one aspect. So each box in this particular flowchart can be termed, or maybe group of boxes can be termed as specific engineer roles that will be present. And that is how people work as a team for one program, one project. So when we move on to this particular oval shape, that is the timing is okay or no, we decide here after the logic synthesis happens, when it's bound with certain constraints, that is the SDC, we decide here based on these constraints. For example, 1 gigahertz clock is there. 1 gigahertz, one specific clock is operating the entire design. It's operating with the speed of 1 gigahertz. 1 gigahertz is equivalent to how much time period? The first typing will be appreciated. Madams and sirs, please, you may need to respond. I think this is a very trivial question that I'm asking. 1 gigahertz of frequency is equivalent to how much time period in terms of nanosecond? I wanted to take this session interactive, but 1 nanosecond, okay. Madam Lalitha Garu, yeah, thank you, Auntie. 1 nanosecond, right? So 1 nanosecond time period that we have need certain gates to pass through, and it is all like the concept of STA would evolve here. That is the pre-layout STA. STA is the static timing analysis, and that we generally deal with delays in the design. So it is all about in the .lib, what is present is the delay that is consumed by each of the standard cell logic gate. It is accounted between two flops. There's a certain number of combinational gates will be present. The logic gates would be present. And that is nothing but between two sequential elements. If the number of logic gates, between two sequential elements will determine the logic depth of that particular design. That is the levels of logic that we have. Based on the levels of logic, our throughput also defines. Throughput is the performance of it. For example, 1 nanosecond can have maybe 20 levels of logic for a given technology. There is a lot of processing that can happen. If it is having maybe 30 levels of logic, that is still a lot more processing that can happen, right? And this is how the technology throughput is defined. For 1 nanosecond, our basic timing requirement will be to check for this 1 nanosecond, is our data being transferred between these sequential elements safely or not at this stage, synthesis stage. If that is not happening, number of levels of logic need to be reduced in the RTL. So this feedback happens here. So if 1 nanosecond is not sufficient for 20 levels of logic, it need to be reduced to 15 levels of logic to meet that particular frequency. That it need to be, the RTL code need to be optimized accordingly. So that feedback need to be sent to the RTL design team so that the restructuring of the code happens. So this is a general feedback that goes in at the early stage of the design planning, whether the timing is okay or not. And then if all the timing is meeting and we are okay with the number of levels of logic, maybe we are safely at 18 or 20 nearly. And for a given technology, again, this need not be a standard number, but I'm giving it as an analogy. And once the timing is meeting, we'll move on to our regular process of physical design or PNR. From there, it begins the floor planning stage. As I explained in the previous slide, it is first arranging the number of memories that we have, the IPs, in a block. Here, the partitioning stage is not, partitioning step is not explained a little more in detail because we are dealing with maybe a block level design. Already a block is present, and traditionally we are talking about a floor planning. So floor planning is like arranging our memories in the periphery, only in the edge in a block, and then planning our IO ports and planning our power mesh. Here we perform our power mesh as well. Nowhere in the flow, maybe here it's not defined, the power mesh is not defined, but we do our power planning also at this stage in the floor planning. And we also put our pre-placed cells. There are something called as the technology will demand for a certain category of cells for the purpose of bulk connection, bulk internal connection for a specific regular interval. There will be separate cells in the library called as the well tap cell. There's a specific cell is called as the well tap cell that makes the bulk connection. All this kind of cells arrangement will be performed in the pre-place stage. Before placement stage, we perform that cells arrangement and the power planning as well. So once this is done, we move on to the placement. So placement is a completely automated process. One single command handles the entire placement step. So that is a completely tool-driven activity. And then we move on to the clock tree insertion. The clock tree insertion or clock tree synthesis, basically CTS, deals with whatever clock that is connected to all of the sequential elements. It need to be planned for balancing. So clock is a single signal that will be planned for a lot of fan out. And whenever we call it as a fan out, is the number of sinks it is connected to. A sink is nothing but the connectivity it is having. So a single signal driving a lot of points cannot be handled in a design. So it need to be structurally planned. So basic structures of clock tree planning would be the binary clock tree structure, or either the H tree kind of a structure, or maybe the multi-point CTS kind of a structure. These are all the different clock tree structure methods that will be practiced in the industry to build the clock tree network. So once this is built, so built and balanced and further optimized also. So we will have metrics like insertion delay and skew to measure upon, and that will qualify and quantify about this clock tree stage. And further we can move on to the timing optimization and meeting the timing aspect, like the setup and the hold time after the CTS. And then we move on to the routing. When so as I explained, the routing is that needs a certain rule type formats. That is the layer map and the cap tables and either the TLU plus format, technology layer formats that has resistance and capacitance information of the material that is used. This is the metal layer, right? So basically, it is having a resistance and capacitance. It has a resistivity factor, and based on that, the resistance will be defined. Any questions you have? Anyone raise the hand? If there are any questions, I can take here.
Participants, please ask questions if you have any questions.
Yeah, if not, we'll move on to. Yeah.
Continue, sir.
Yeah, thank you. So in the global routing, we also have specific file formats, like we perform the extraction. We call, once the routing is completed, we perform the extraction of the metal layer information with certain input files. Extraction is extracting the resistance and capacitance information into a file format called as the SPEF, standard parasitic extraction format. And usually SPEF and netlist will be used for post layout. This is all a layout that we perform, and the post layout timing analysis, we use these inputs. Basically, this timing analysis will be performed in sign-off tools. Again, the sign-off tools will be separate from the implementation tool. So basically, the implementation PNR implementation tool will be from the Cadence. It's basically the Innovus we generally use, and from Synopsys, it is predominantly in the industry. It is being used the ICC2 in the current times, and in the Cadence, from the Cadence, the Innovus is generally being used for implementation. And even in the sign-off check, there will be different sign-off tools. Like for the timing sign-off, we will be using from the Cadence. There is another sheet that explains the different tool suits that will be used for different job role or even different activity, right? That will go through. But here, once the routing is performed, extraction will be done, and extracting the data, we will check the real delay values in the nets as well as in the cell delay values will be coming from the timing libraries itself. So when timing is okay, we will proceed further for the post layout STA verification and fixes. But if timing is not okay, we may need to go back to again the initial placement stage. We may need to correct our placement with certain techniques. Other techniques will be present here, like certain bound creation or maybe path group weightage provision. All of these techniques will be present here in the placement. If not, the CTS has a skew and latency or insertion delay very much bad. It is not good at this stage. We may need to correct that with certain balancing techniques in the clock tree. And if routing has any congestion issues, routing metric is measured with the term called as congestion. So from placement itself, we measure this metric called as congestion, and the congestion will be measured across all of these stages until the real routing happens. Yeah. So as Radhagar also mentioned, and there will be another metric that is called as utilization. That is how much area is being utilized in terms of the placeable area, right from floor plan stage till the routing stage. Utilization gradually increases when the design utilization increases. Yeah. So these are all the different parameters or metrics that are used for measuring and having the language of backend implementation usually. So these are the terms that will be used. So once the routing is performed, even the same formal verification step can be performed. Usually, since it's tool driven, tool will not mostly perform mistakes unless some handling or switches is inappropriately used. Only then the formal verification might go for a toss. Usually, if it is the logical equivalence will remain intact, but timing need not be always clean after this stage. So there will be back and forth happening here for a couple of cycles for a given design, and that is how we need to make the design prepared and ready for a timing cleanness, and then we take it for post layout STA. If you have any questions, you can ask me here until the post layout STA stage.
Sir, I'm Dr. Leela Rani.
Hello, madam.
Sir, as we have, sir, as we have various domains like RTL, RTL design, verification, physical design. So students are getting opportunities in various domains like this. Few are getting actually the custom layout as a custom layout designer also. So how about the career growth aspects of a custom layout designer compared with other domains, sir, in industry?
Compared with other domains, right? So
other domains means like if a physical design engineer is there, or maybe verification engineer, like those who are doing SV or UVM. So what are the career growth aspects of if a student joins a what is this custom layout designer as a custom layout designer?
Okay.
If any person joins as that in that role, what about the career growth aspects, sir, in industries?
In industry, basically, if one has to begin with one specific role, so to know a little more about the technology, in my viewpoint, I would rather begin as a layout engineer only, custom layout engineer, or to explain about my experience, right? I have even initially worked as a layout engineer to get more exposure on the way the transistor for a backend implementation engineer. It is always very much good to know how the layout basic structure is present, basic layout understanding should be there. So it would be very much easy for them to cope up with additional advanced topics. So what happens is in the backend digital design, there will be areas like STA. There'll be basic first initial area will be synthesis, and even physical design or STA, LEC. A lot of people would be confined to one particular role for years and years. If they are very much comfortable in doing the same process, repetitive job for any of the programs that they're assigned with, only one role, they'll be limited to that or confined to that piece of knowledge only. It has been a boon for me. It has been a blessing kind of thing. I was able to explore every nook and corner in the back end and able to deal with designs at different level as well. So through my experience, I could say it is nothing wrong to begin as a standard cell layout engineer, but do not end up there itself for any of the budding aspirants.
So in the later stages, they can switch on to other fields like either physical design in the back end also.
Definitely there can the internal switches can happen, but even we should
mostly no, sir, in the front end, if they start with just now, as you said, if they start as an RTL engineer, they'll be they'll be sticked to that particular role only.
Correct.
Like in the front end.
But it need not be necessarily that one, madam, because there might be certain designs, very small designs. Basically, one company, they make only UR or I2C basically.
Okay.
that is a small piece of work, right? So they can code their RTL, they can verify their RTL, they can do their synthesis, they can do their PNR. One engineer can do all of these aspects.
Okay. Okay.
It is a big SOC we are talking about, a massive SOC which has all the protocols, NOC, AMBA, everything. A lot of work is there. There may be 500 engineers working for one chip, spanning across front end, back end, DFT, packaging, and post silicon validation. There need to be an army for this.
Yes. Sir. Okay, sir. Thank you.
Yeah, thank you. Yeah, that's a good question from Professor Leela Ranigaru. Thank you. And any other questions similarly from anyone else? If not, we can move on to the next data. It's nearly 8:45, I think, right? And so Venkatesh Garu, it is up to 9:30?
Up to 9, sir.
9, okay. Then we'll wrap it up quickly. Only 15 minutes, right? So I have few other slides.
So you can extend up to
It's for
9:30
the-
also,
Yeah.
or you can leave some session for interaction.
Interaction, yeah. I'll there are a few other slides similar to what Madam Leela Ranigaru has asked. I put up what are the benefits out of this industry, and even the tools aspect, right? That will be covered, like which area, which tool is specifically used, and where that expertise need to be built. That will also be covered here. And fabrication, I have put one slide about this to quickly explain. This is more of, I think our academicians will be able to excel in this. So this has been always existing concept, right from sand to silicon. How do we bring this up? All of these lithography techniques and chemical mechanical polishing and all of this will be well explained by our faculty friends themselves. But I'll move on to the next detail. If you have any specific question on this, about this, but as of now in India, we are lagging behind in this area because there are no fabs. We do not have people working in this particular sector, chip making itself, right? And the fabrication unit, it only happens to be, it was there earlier, maybe a couple of years back, it was in IIT Madras, and their MPW format, they process the chip. Clean rooms, basically. If there is no exposure to these clean rooms, we may not be able to enter and get to gain the knowledge. Now that we are blessed to have the new organizations picking up this piece in the India itself, building the fabs, and let's see in the future, a lot of technology can also be absorbed in this. In the wafer bring up, basically wafer to chip bring up, that is the entire fabrication process, right? And next I have about the job roles and EDA skill set to have. So this list is compiled through a little research on my side, and this is exhaustively what is predominantly used from the 3 different vendors. And the front end side from the Synopsys, Cadence, and Siemens. These are being used. So we have different roles like the design engineer, RTL IP design engineer at a block level, and that will further be, all of these pieces of code will be integrated by the RTL design engineer in the front end. Similarly, we have the IP verification engineer and SOC verification engineer. So basically, the verification engineers will have different. The team will be very bigger size. Usually, for a given project, majority of the team members will be verification engineers, thoroughly verifying the code, and even the validation engineers. So basically, the validation, like in the FPGA, it will be checked. The prototyping will be checked, and it will be handled in a different tools for the simulation purpose as well. And emulation is again another new in the nascent stage. It is a technique wherein we check, and pre-silicon only we will be able to assess on the performance. Similarly, on the front end, we have the DFT being dealt. So in the RTL itself, we have a technique to put the DFT features in the RTL code itself. That is why DFT is put in the front end as well. So there are separate tools to deal with this DFT as well. And similarly, the formal verification. The formal verification is also performed on the front end side once, and even at the back end side, it will be performed. But these are the usual tools that we use. And the post-silicon validation is after the silicon bring up happens, after the packaging and silicon bring up happens, the validation need to be checked on the bench. So that happens on the PSV side. This is all the front end job roles that will be present. And even in the back end, there will be team members like on the full chip on design planning, the synthesis engineer. This will be very high level experienced team member who will be like planning on the design aspect in every, we're considering every points of implementation, like be it on the IO planning or partitioning, be it on the packaging planning. So basically, if it is a flip chip or a wire-bound kind of a package, everything need to be planned accordingly. And this will be performed at this stage by this particular senior most engineer. And then block level implementation will be performed by each block owner, block engineer, and then STA sign-off engineer. These are the tools that will be used for STA sign-off. And for the here the sign-off backend sign-off purpose, another player has been included here. Usually, this is for the most predominantly used IR sign-off tool in the industry. And power analysis is again another aspect that will be dealt maybe in detail in the further discussions that you'll be having in the next couple of days. Power analysis is again estimating on the power the design is consuming. Basically, it's termed in terms of the watts, milliwatts, and that will also be accounted for the purpose of IR robustness analysis. Similarly, physical verification tools will use them, and parasitic extraction, as I mentioned, RC values will be extracted with these tools. IR drop predominantly with this, and analog layout is the custom layout will be performed by these tools. Mixed signal design will be performed with this. This is again on the design aspect, analog design aspect. So these are the different tool suits that will be used. If you have any questions, you can ask here. I'll be able to take. Yeah, if not, I'll move on to the next slide. That is the breadth of the industry. So basically, I have try to put all the different organizations that will be involved in each aspect. Like there are product companies, there are product startups, service-based companies, and the foundries that are already put in the pyramid, and even the IP vendors which are present, IP and the EDA vendors. So this is a little more informative, but as there are certain questions about what an aspirant can be looking in for, and basically how it would be for an engineer to be in the VLSI career path, right? For an aspirant to be in this particular field. It will always be very much exciting, as I would say. It brings in a lot of challenges in everyday activity, day in, day out. It will be very much interesting and informative. We need to keep ourselves very much updated about the evolving trends and technology, and as well the implementation techniques, right? Every day will bring in a new challenge. It's not a repetitive work that will be confined for, but any role that we play will bring in a new challenge. Every design will be different. Every project will have its own unique set of challenges. So it's very much interesting area, and hope this same interest will be carried on to the aspirants as well, to the young students that you have in your classrooms. Yeah, I think that is all that I have. Maybe If any questions, I'll be able to take up, and then we can maybe put the next 10 minutes or 15 minutes for the question and answer discussion. Any specific questions? The details of maybe the entire aspects will be covered up in the next things. That is what I was informed. And this is an overview or outlook perspective for the 2-hour long discussion that I tried to put up. It's an overview only. Yeah. Any questions I'll be able to answer.
If anyone want to ask any questions, you can raise your hand or you can unmute your mic and ask the question.
I think there are certain questions being typed in, but still, this is a forum to have in our interactions or getting to know or sharing the knowledge with the faculty forum first. About the students, maybe it is specific to each organization's commitment or restriction, right? That could all will be dealt with the placement coordination team and for the internship or maybe the other aspects, right? That will be dealt like that, I think, right? And anything in the technical aspect, do let me know. I'll be able to help or provide the necessary knowledge that I'll be able to help with.
Anyone want to share any feedback?
Did I go very fast or did I match up to your expectation? Or you can put up that kind of feedback, or maybe do let me know. Maybe it will be helpful for my future presentations or anywhere that I go around and present, right? It will be helpful for me as well, I think. And I especially want to thank all the faculty experts here who have joined here today, and for allowing me to present this part of knowledge that I have. And definitely, I look forward. And basically, I'm also from Vizag, to tell, right? My native is Vizag, but still, I'll be going around different places to have my work finished. Wish will have maybe some kind of personal interaction if our paths cross through. And yeah, I think if no questions, I'm done from my side. But if there are any questions, I'll be able to take. Yeah. Was it relatable? It was clear. I am very much grateful about it. But was it relatable? We're all from the VLSI fraternity, right? A lot of these topics which were covered, which were discussed till now, were there a part? Were all of them a part of your day in day out work, your curriculum, or anything additional? Also, I was able to convey. Because a little advanced topics might be covered in the upcoming sessions, but I was able to touch base upon certain aspects. Only overview. Okay, great, Madam Jasmine. I think we can wait for another 2 minutes, maybe.
Yes, sir. Yes, sir.
In the interest of time, by 9 we'll conclude. But if there are any questions for the next 2 minutes, I'll be able to take.
Sir, thank you, sir. It's a good presentation, sir. Nicely, you have covered all concepts from RTL2 till GDS2. As you have mentioned, a few concepts, of course, we have covered in our regular curriculum, like in VLSI design and system Verilog, and even in the physical design, and few more, of course, the overview you have covered, sir, definitely. We got to know definitely all the concepts overview, sir, from RTL2 till GDS2. Thank you, sir.
Thank you, Madam. Thank you very much.
Dear participants, all of you switch on your cameras to take a group photo. Participants, if possible, please switch on your cameras to take a group photo. Okay, thank you, everyone.
Thank you. Thank you, everyone.
Dilip sir, thank you, sir. You have explained in detail and very clear flow from RTL to GDS, sir. Actually, we all know that flow, but you are given very in detail information. Like we know that flow like a picture with 320 megapixel, but you have given like a picture with 1080 pixel. So we have enhanced our knowledge in that particular flow, sir. Thank you very much.
Thank you. Thank you, sir. Thank you very much. It's my pleasure
Thank
to
you, sir.
share this evening with all of you. And yeah, wish you a very pleasant day ahead. Yeah. Thank you very much, everyone. Yeah. Bye.
Thank you, all the participants. The feedback link is in chat box. All of you can fill your feedback link. According to that only, we will give your attendance. Once again, I am sending the feedback link.
Thank you, Dilip sir. This session is very informative. In addition to the technical content, your insights into the various job roles in RTL to GDS, such as RTL Design Engineer, provided the participants with clear roadmap for career opportunities in this domain, sir.
Thank you. Thank you, madam. Yes.
Thank you, sir. We look forward for your sessions in our future endeavors.
Thank you. Thank you, madam. Sure. I'll sign off for the day. Then thank you.
Thank you, sir.
Yes, sir.
Thank you.
Thank you.
Thank you. Thank you.
All the participants fill feedback form and leave the session. Madam, recording off చేసిన మేడం కృష్ణవేణి మేడం
సార్ చేసేయండి సార్.
ఓకే ఓకే